So we're going to talk more tonight about digital elevation models, and we're going to continue that discussion. I said talk about uses of digital elevation models. That was the discussion that we had 2 weeks ago prior to spring break. And then we will talk about error and data quality. We may finish that tonight. I think there's some slides on that topic spill over into next week as well. That sounds like a funny topic, but it's actually very important. You know, when you're in school and you work with these great labs that have been prepared for you, the TAs are great, all the data sets are pre-packaged and work perfectly and everything works. The real world doesn't work that way. You're dealing with incomplete data sets. Someone gives you data sets that are incorrect, incomplete, all sorts of problems. Not trying to discourage anybody, but we'll talk about that the second half tonight and then next week, about different issues with data quality you'll encounter and what you can do about that. But first we'll talk more about TINs and digital elevation models, the conversation from 2 weeks ago. We talked a little, I think this might be a review. Right at the end of the course we talked about a TIN. A TIN is a triangular irregular network. It's a way to model topology. It's a vector data set, though it can often be derived from a raster. I'm just going to go right to the next slide. I think that might explain it better. So a TIN is a data set that manages information about elevation with triangles of equal aspects. So this equal aspect and slopes. So this piece of land in triangle H is flat, but it's leaning. It's flat within the triangle, but it leans a certain way, which we call aspect. Slope, we'll talk about this in a minute, but I'll start. Slope is the grade, the 5% whatever, that the land trends up or down. You might see that on a highway, on a steep decline. You might say trucks caution and slope 5%. That's what we refer to as slope, is the elevation change over a horizontal distance. There's a slide on that coming up. Aspect is the direction. So if this is, a good example. You're driving down to Lake Erie from here. You're driving Buffalo. Let's say it does this. So here's UB, and here's Erie Basin Arena. You ever notice coming into the city we're quite a bit higher here. If you drive down Main Street towards downtown, you can kind of see the top of some of the skyscrapers. And we're actually as high as some of the skyscrapers here. So if you were driving from here, there's a certain slope from here until there. Or just maybe it's easier just to think about driving down a hill. So the slope is the change in y over the change in x. If this is a mile and over a mile, you descend 528 feet, there's a slope of 10%. There's a mile 5,280 feet. So over that 5,280 feet of horizontal distance, in this diagram you descended 528 feet. So there's a 10% ratio. Does that make sense? That's called the slope of the topography. The aspect is the direction. Say we are walking, this is UB and that's Erie Basin Marina, you're walking basically southwest. So the aspect, the direction the land is facing, is southwest. That's the aspect. The aspect is the aspect gives you a direction. The east facing land, north facing land, and so on. So in a TIN, these triangles have an equal aspect. This land face slopes southeast, that land slopes northwest, and so on. Yes, the topology of the TIN is important, but that's the key point. If you take away one thing from this, I would want it to be that. But the TIN is a vector-based model of triangles that have an equal aspect. And you put these triangles together and they model a slope. See if I can bring up And it's called an irregular network because the triangles aren't the same. I mean, the shape of the triangles depends on the lay of the land. So here's TINs. There's a generalized picture of a tin. Notice the triangles are irregular, as the name implies. I think there was one more on Google here that is exactly what I'm showing. They put the hillshade over it. Wish it were bigger. Yeah, bigger. That one over. So notice there's triangles on this. They put the shading on it to make it visual. So you put the triangles together. Here is a triangle that faces this way off the mountain. I don't know what direction it faces way off the mountain. There's another triangle that faces this way. But each triangle is flat. There's not any elevation difference within the triangle, but it faces its aspect. It slopes a certain way. So this is a picture of a real-world tin with a mountain in the middle. It demonstrates how the tin models slope and aspect. So here on the top of the mountain, there's that piece of the mountain faces towards us. That triangle over there represents pieces of the mountain that face away. So I think that's the best take. I usually will ask a general question about the tin, about what it is, what it represents, rather than having you memorize it or describe the exact topology. It's very efficient because kind of like what we talked about, it's a vector model, but kind of like what we talked about with rasters, you can use bigger triangles in areas where there's little change. So it saves a lot of space if you think about that. I don't know if that screenshot shows that well or not. It kind of does. It's kind of hard to see. In the areas that are flat, we model them with bigger triangles. That's an efficiency, where areas with high changes in elevation, you use the smaller triangles where required. So that's a storage efficiency. Difficult to process is a disadvantage. It's a complicated algorithm. Luckily in 2015 you don't have to do it. ArcGIS will do it for you, but ArcGIS has to work hard to do something like that. It's a complicated algorithm to come up with something like a tin for the computer program. It models breakpoints and ridges well. So if your elevation data has features like ridges, breakpoints are features in which can be geologic features as well, where things don't tend to cross. A ridge is probably the best example of it, or mountains. Tins are very good at modeling that type of feature. So where do we get digital elevation models? We'll spend a little bit of time now talking about the process. And often they can be derived from existing contour maps like USGS topos. Vectors, such as contour lines, we talked about that the Tuesday before break, can be used to derive digital elevation models. Specifically the equipment that can be used, we can derive digital elevation models from aerial photography, from orthophotography. We talked about orthophotography a bit when we talked about remote sensing. Here is a stereoscope machine. No one does these things. There are still people that do these things. It takes a special kind of concentration. Because basically this is like related to the 3D glasses. I don't know if any people still wear those. It's a 1980s thing where you ever put on the 3D glasses and go to a movie and everything jumps out at you? Well, these stereoscope machines do the same thing. And if you look, he's looking at two photographs, and the machine allows features to jump out, and there you can see the elevation changes on the photos. And then some very patient individuals go through and create contour lines and create elevation models based off these. That really takes a patient person to look at those in 40 hours a week. It's not something I could do. But the stereoscopic aerial photography is a more traditional way this was done. Satellite image, companies like Pictometry, more modern, are using computers and sensors to do this. Where do digital elevation models come from? Again, existing DEMs come from state agencies. In this country, the U.S. Geological Survey, USGS, creates a lot of data. I'll go to this link in a minute. Private vendors, we've done that. You can contact private vendors and have them fly over an area and go through these processes to develop a digital elevation model. You might do that because you want something in greater detail than the USGS provides. And I think I mentioned this more and more. This can be done quicker than I ever could have imagined using drone technology. You can purchase a drone that actually will go out and remote sense the area below it and provide a digital elevation model of the area beneath the drone sample relatively quickly. And I think for 30 or 40 grand, a company can purchase a drone and do this themselves. Things are rapidly changing in this arena. We purchased a drone to do remote sensing, not a cheaper one for taking pictures on sites. We were playing with it over the spring break at work, and kind of a whole new world that's coming. The things they look like Star Wars or something. They scare me. I'm too old. But one example we would use it is if we want to do a biological assessment of someone's property along a proposed pipeline. A lot of people don't want, strangers traipsing through their backyard, and the thinking is, we'll see, they might be more comfortable with someone remotely flying a drone in to take photography and leave without having, the disruption of a bunch of humans walking around your property. I'm not convinced people that don't want people on their property will totally be okay with someone flying a drone over their house, but that remains to be seen. Whole new world. I think we looked at that last week. We'll come back to that in a minute. So the USGS, this next section of this next topic is specific to this type of data available in the United States. Other countries have their own programs, of course. But the USGS has different digital elevation models that correspond with topo quads of a certain scale. So the smallest USGS topo quad that's out there is a 1 to 24,000 scale spatial map, where we talked about scale early in the class. So on a USGS topo quad, every feature is 1/24,000th of its real world width. There's an example of that. Let me go back. The light from that is at a perfect angle, so all I see is glare. So these changed. We looked at this in some context already, I don't recall which. These are, when we were talking about contours, these are the 1 to 24,000 foot, 7.5 minute USGS topo maps that you see pictured here. And their boundaries are also visible on this map. Here is and each one has a name. This quadrangle, this topo map is called Clarence. There's one called Lancaster, Buffalo, Northeast, Clarence Center. That'll all be familiar if you're from here. And the campus is in a quadrangle called Tonawanda East. So when you order these maps, they are at the scale of 1 to 24,000. And they're, notice it also says 7.5 minute map. Remember those, we talked about degrees, minutes, seconds, right at the very beginning? So the width of these maps is 7.5 minutes. So that's where that comes in. So this ESRI's kindly stitched them all for us rather than having to order in separate. There was a day where we'd have to, every time we had a new project, we had to go on one of these sites and order each of these maps separately. Now you can just bring the maps in the background. So this relates to DEM, is that these 24K maps were used to create a DEM at that scale. And for my example here, I show, this is up in Niagara County, just north of us. Here is a screenshot of a digital of 1 to 24,000 quad and the DEM that resulted from it. And I believe that creates a 30-meter DEM grid. Now in this case, the DEM is a raster. I talked about rasters earlier. So there's equal cells. It's hard to see here, but there's small cells with pixels, like we asked on the first test. Each one of those would be, actually I think it's 10 meters cell size. So obviously that gives you a sense of the accuracy of these DEMs. You would get a cell every 10 meters, every 37 feet or so. And then just one elevation average for that distance. There are also 1 to 250,000 foot U.S. topo quads. USGS topo quads that, in fact, if I zoom out, this will automatically switch. These are 1 to 250,000 foot maps. They cover a much wider area. They cover 30 minutes or half a degree. Half a degree roughly corresponds to 1 to 250,000. And so most of this area falls within a 1 to 250,000 map called Buffalo. The one just to our north is called Lockport. Actually, the campus might actually fall within the Lockport. It does. Lockport map. Some of this area might even fall within a Toronto map. The line between Pennsylvania and New York is 42nd latitude, and 43 goes right through Grand Island just about at campus. So you can see 30 minutes makes sense. 30 minutes is half a degree, and there's 2 maps between here and Pennsylvania because they're each 30 minutes, Buffalo and Olean. So they're even in that. I'm going to get into the arc seconds, but because of the source data, the more zoomed out maps, as well as the 1 to 24,000 foot maps, are sources for the DEMs, and this ends up creating the USGS National Elevation Data Set. Covers most of the country now in this seamless database. That's relatively recent. The map shows us where we have. They're actually down to 3 meter in a lot of the country, and 10 meter in most of the country, or all of it maybe now. They have these digital elevation models down to 3 or 10 meter cells or pixels. That's actually fairly recent. You could never rely on this widely available amount of data before. Are there any questions? So let me show that website again. It's ned.usgs.gov. And another website is the national map. That's what I was trying to find. It's actually a good resource, not just to show you in class, but for your own benefit. It's viewer.nationalmap.gov/viewer. Well, this time there's no government. Last time I taught this class, there was a government shutdown. And they actually, remember that a year and a half ago, and they actually took the sites down because the government wasn't running, so they took the web pages down. So I wasn't able to show this. Everything's back to normal since then. So here, I can zoom in and get information on this national map about availability of topo maps. National land cover, elevation index, and so on. Not the fastest website ever made either. Yeah. You probably shouldn't be too surprised. Yeah. And it also doesn't seem to be working today. I turned on the topo availability and I don't see, unless I'm missing something, I don't see the boundaries. That's great. You can see, I don't think we'll be able to see, oh, it shows you where, just in all one color, where different DEM products are available. If I click identify. No feature selected. It doesn't always work great. Moving along. A DEM is one of the more widely used sources of data. That's why I make sure to talk about it. That you would do in GIS. It has many different uses, including beyond what I've talked about here. If you just think about that being modeling the Earth's surface and elevations, I think you could probably come up with a lot of uses on your own without this. But just some examples of different types of analysis. Viewshed analysis, for example, if you think about it models the surface of the Earth, you can then build a model to see where things can be seen. If this is our side view of a DEM, a common analysis is called a viewshed analysis. We can model that, if I am 6 feet off the ground here, can I see, do this? I can see that point, but I can't see that point. Viewshed analysis. And we're doing less of this than we were maybe 4 or 5 years ago because some tax credits are gone. But there was a lot of wind farm development, maybe in the late 2000s. And our company did a lot of work helping to site wind farms, the environmental concerns from the development of a wind farm there. Obviously it's clean energy and that's good. But they can be deadly to migrating birds and bats as well. They're also a visual eyesore. And if there's a nice national park, you don't want to take the kids across the country in the Grand Canyon and your beautiful vistas ruined by 100 of these stupid things spinning around. So we were often asked to do a viewshed analysis. Like say if the wind farm, that's the worst windmill ever. If the windmill is here, where could it be seen? Can it be seen here, here, so on. There's also, it's something I wouldn't have thought about, but it actually makes sense. They're spinning and they're metallic at the right time of day, like maybe just a half hour ago or so. It can cause reflections that can really bother people, especially people with epilepsy. Can be lured, or I don't know if the word, into a seizure. Because think of a disco or a club with the ball spinning around. Like many years ago, they don't still have that. The turbine spinning can cause what's called a flicker problem, where the sun reflects off the turbines and causes a pulsating light, which is, at worst, could affect someone with epilepsy. At the very least, it's really annoying. So you can use viewshed analysis, a specific type of that, to determine where the flicker would happen. Let's say it happens here. If you've got houses there and there, you want the flicker to happen here, not here. So every time these people sit down for dinner at 5 o'clock, they have to deal with a pulsating light. So DEMs are used with this viewshed analysis on these wind turbines to make sure to minimize that health concern for the public. That's one specific thing that we got into quite a bit that I had never heard of anything like that before. Contour mapping, there's a million uses for that. You can use the DEMs to develop land contours, hydrologic modeling. I don't have that listed here, and I should. Where is the flood potential? What is a river's watershed? You think about that. And if a flood hits, we've done this work for New York City, for example. if a Category 3 hurricane hits New York City, and it did, and Hurricane Sandy, what will the inundation be? Everyone was warned that it would be bad, and it was. If you were down in that area during that horrible storm. And the DEMs were used to predict the areas of inundation based on a particular type of hurricane, what the tide would be, and so on. So hydrologic, both in the sense of agriculture, flooding, but also things like hurricanes. That makes sense? Display for visual purposes only. Sometimes just displaying the land surface on a 3D map for a public presentation. We've done that where we've developed flight paths. I wish I had that. Sometimes I'll show that. We developed flight paths over a military runway. We don't develop them, we map them so people can see how planes and helicopters approach. But we also, rather than just showing it over a flat surface, we can show why they come in a certain area based on the topography and so on. I do have watershed analysis here, so I can mention that. So the analysis of where water comes from, what land mass contributes, say, to the Niagara River, to the water that ends up in the Niagara River, the Genesee River, Hudson River, and so on. And those are called watersheds. DEMs are used to derive those watersheds. So not just for flooding, but for pollution. If X river is polluted, where is the pollution coming from? If there's a polluter that's not in the watershed, that polluter is not contributing to the pollution. If other polluters are in the watershed, that's a possibility that needs to be looked at. FEMA actually has a cool tool called HAZUS that uses digitalization models to map potential for destruction in earthquakes or hurricanes or floods. I think most often used for floods. And we've done some projects where you put in information about the cost, the value of things in your area, the value of homes, hospitals, and so on. You input a digital elevation model, and then you input an event, like a rainstorm of this severity will happen, a hurricane of this severity, and it will predict the damage. And that Hurricane Irene happened when we were supposed to do our final presentation. It was a little bit of irony. The final presentation was supposed to be in Utica. Right after Hurricane Irene, we couldn't make it because it was flooded. And actually, the HAZUS model predicted the flooding pretty well. No one expected to be using the predictions so quickly like that. Do you have any questions? Volume estimation. I'm mentioning some really cool, complex things, but sometimes the answer that you're looking for is simple. What is the volume of a hill? In a very simple question, in our work for the Water Authority, we used a DEM that they had created. They had a big pile of dirt they wanted to cart away, and they wanted to know how many dump trucks to order. It's nothing as fancy as modeling Hurricane Irene or something like that, but it was still a problem where they used GIS and DEMs to solve the problem. They had a model of this hill. It was from construction of various sites, and they used the DEM to estimate how much dirt was in the pile, so they knew how many trips in the truck to remove that volume estimation. Not only that, but for fill, if you want to fill in this depression, how much dirt do you have to put in it? Volume estimation, either in removal of elevation or filling. Not the most complex analysis, but something where it would be useful. Here's some screenshots of 3D viewing of models. This is, I bet that's got to be Southern California. They're taking reality and modeling it with a digital elevation model to view changes in elevation over the land surface. That sometimes it's not necessarily analysis, but just for presenting something to the public. So DEMs allow you to create maps with a third dimension on them for display. This one I like. Everything I've shown here or talked about has been literally elevation. You know, the National Elevation Data Set models the elevation of the surface of the Earth. We talked about volume estimation, you know, actually taking a pile of dirt away or creating contours, you know, mapping a hurricane. So those are all literally elevation. But a digital elevation model can be created using a surface that doesn't necessarily represent literally elevation, but the density of occurrence of any event in any spatial event. And this is the PhD project undertaken by, you know, a graduate of this department, the geography department, mapping crime in the city of Buffalo. So there aren't actually mountain peaks here in the city of Buffalo. Those are areas of high crime. So it's a visualization not of the actual surface, but of areas where there was higher crime activity. So here is the raster surface on a 2D map. So this comes in 3 stages. Here, there's a point file of every crime that occurred in the city of Buffalo. I don't know what time period he chose. There's some geocoding problems, and there's some outside the city. But, so he converted this to a raster to show areas where there's higher crime density. So if we had eight crimes there, 4 crimes here, 2 crimes there, the process of converting from vector to raster. We'll talk more about those type of analyses probably next week or after the test. The process of interpolating this to a raster would then create this into a raster with cells with the value representing how many crimes. Does that make sense? That also helps us do something called spatial interpolation, which we'll talk about, where we try to predict. You can use the raster model to predict, okay, if there are crimes here and crimes here, there's no data. Would there be 7? Because it's between 8 and 6. So we'll talk about that more later. But this is the process of taking vector points and creating a raster surface. That's what he's done here. But then, would you agree this is easier to visualize? I mean, he's actually taken this and made it into something like a digital elevation model where we pretend that this has an elevation of 6 feet and this has an elevation of 1 foot. And then you can exaggerate the model. Say, well, multiply everything by 10. So instead of 1, 1, it would be 10, 10, 80, 60, and there's his result. So it's not a literal elevation, but I think he's very effectively shown areas where there unfortunately was high crime in those cells or pixels. Something that's very difficult or impossible to determine. I would say just look at the dot map of where crimes occur. It's pretty much impossible to determine that. This was taken over such a long period of time that it's basically, it doesn't look good, but there's a crime everywhere. This might have been over years. But what you can't tell in here is maybe in that location there's 1 dot, and here this location there's 50. You can't tell that. By converting it to a raster surface and then making it into an elevation, that becomes a lot clearer. So the key takeaways here are the conversion from the vector to raster. We'll talk about that further. And the fact that don't think of digital elevation as just real world topography, that there's a lot of other uses, especially with visualization. One area, and I know we'll talk about this more, is chemical. I chose this was a cool project that someone in our department put together. But one area where this is used a lot would be chemical concentration. Mapping areas where PCBs, like at Hudson River, areas like that. Here is, I guess I already drew that on the screen, but here is a depiction of the viewshed analysis. This is the person, you have so here's the digital elevation model that was used. Here's the person may not be on the ground. Even if you're standing on the ground, you're 5 or 6 feet above the ground, depending on your height. Or the lookout may be from a building. I mentioned viewshed in conjunction with something bad, seeing windows when you don't want to see windows. But we do the analysis in the reverse. If you are locating a fire tower, you want the forest ranger to be able to see as much of the national forest as possible. So you want to find an area where as much is visible as possible. So this is a viewshed analysis showing that this person there can see everything here from this tower. They can't see this or that. That kind of seems weird. You wouldn't think they'd be able to see that. But because of the slope, the aspect of the slope, this second area of white is visible from that tower. That's another viewshed analysis specifically called line of sight. We also, I think they use internet. I'm dating myself like I always do. But we did a line of sight analysis for Erie County Water Authority because they communicated to trucks by radio. Does anyone remember radio? So they needed to place their FM radio tower on one of they didn't want to lease space. Sometimes people, they'll pay 103.3 The Edge or some radio station to put up, hey, can we put up our transmitter on your tower? They don't want to pay for that. The Water Authority has these big tanks, the big blue water tower on the Youngman. That's where they store all our water. So they said, well, we'll just put the transmitter on top of one of our tanks. We already have these. Which tank would have the best line of sight to the whole county? So that was an analysis we did almost 20 years ago, where we took the height of every one of their water tanks and analyzed what percentage of the county was most visible. And the answer, if you're from this, how many people are from Western New York? I'm curious. Okay, that's good. I'm always glad to see that. You might not be surprised if you're from this area that it was a tank in Concord, south of East Aurora, where the elevation is very high, and if you go to a hill down there, you can see almost all of Metro Buffalo from up there. Now I think they use an LTE or 3G signal from Verizon, just communicate that way. But this was before that. Here's another example I put up there, a digital elevation model overlaid with a actual air photo to create a very realistic surface of this mountain in China. And it's a digital elevation model of the terrain in China. And an infrared Icono satellite. We talked about satellite remote sensing before the break. Those two things combined give us a really cool, really realistic view of this particular location. That's the end of that topic. It's still kind of, let me think. We'll go a little while longer maybe, and then we'll take our break. We're not quite halfway yet. Are there any questions before we switch gears? We will revisit these topics specifically in regards to spatial interpolation later. Talk about vector to using rasters to interpolate. But for now, we're going to switch gears for a while. There's no questions first. And as I mentioned, the next big topic we'll talk about here is data quality. Why is data quality important? Hopefully you can all answer that. Obviously, I know I have a slide on this. The whole The rest of this lecture will all come back to this: why is data quality important? And this acronym. Has anyone, you may not have, has anyone heard of the acronym GEO? Garbage in, garbage out. So you can summarize everything we're talking about data quality. Why is data quality important? Any analysis you do is only as good as the data you use. And an acronym, I often will ask what that acronym is on the test. GEO, garbage in, garbage out. So all these things, this analysis is great, but if the DEM's wrong, my analysis is wrong. Think about it. Your analysis is only as good as the data that you're using. That sounds, if these crimes are mismapped, and in fact, I don't want to pick on, but this is only the city of Buffalo. Some dots appear to be outside of the city of Buffalo. That's probably an error. And because of that, we see some crimes showing up out here that probably were somewhere within the city. Because the addresses that he was dealing with, or she, I'm not sure, I don't know this person, the addresses that we're dealing with probably have mistakes in them. So garbage in, garbage out, in the sense I'm not calling the project garbage, but hopefully you understand what I mean. Your output analysis map or so on is only as good as the data you use. And so that's why data quality is important. That sounds simple, but it's not. There's a lot of nuances to this, and that's what we'll be talking about today. Just what is quality? It becomes philosophical a little bit. Just what is an error? Because in many things we'll see, it's not necessarily the data that's wrong, it's how you're using it that's wrong. It's not as simple as just something being wrong. And as I said, this is something we deal with all the time. And I always make sure to stress it, because as you go through, whether it's a class at UB or you go to an ESR training class, all the data sets are nicely scrubbed and work perfectly, and everything in there is perfect, is filled in, and the real world's not like that. And we'll talk about the ramifications of that. So here are some original first concepts that we'll talk about as far as data quality. Data accuracy and precision. I'll start with precision. Precision measures how exactly is data stored. If we see here, I found this from an ESRI class. When we talk about projected coordinate systems, here's a projected coordinate system. If I were to map, in this example, I think they're mapping Chicago. And in this map, Chicago is at a coordinate of 7, 13.5. Is that wrong? You wouldn't call this wrong. I could go to 7 and 13.5, and there's Chicago. Would you consider this precise enough, to put the coordinates in your Garmin? Probably not. You might end up in Lake Michigan or Wisconsin. But it wouldn't necessarily be correct to say the data is wrong. It would be more accurate to say that the data is not precise enough for what you need it for. Do you understand the difference? If you're going to visit your relatives in Chicago, you don't open up a world map to try to get there. You open up a map that has the correct precision. No one has a map anymore. But you would load into your Garmin a street map of Chicago. This map is not very precise. But if your goal is just to locate Chicago on a world map, in that particular instance, it is precise enough. If you want to go to a Cubs game for opening day and it's not snowing, that's not precise enough. So the other point there is the level of precision that's there depends on the purpose of your data. So while it's not wrong, it may not be precise enough for your particular needs. People make this mistake all the time. I feel bad for one of my GIS analysts is down in Florida. project manager gave them a map. I don't even remember what the features were. They might have been roads of the state of Florida off of a state map. It said, please digitize these. They're actually pipelines. And so we digitized, we'll have some slides talking about this coming up. Digitized the map off a map of the whole panhandle of Florida, gave the GIS data set to the project manager. He comes in all angry the next day. These aren't right. He tried to line them up exactly with other engineering data, expecting them to fall exactly where they are in the real world. It's like, well, no, I traced them off a map of Florida like you told me to. But the precision on the source map was not good enough. It would be like me saying, could you find Buffalo? That'll be the exam question. Make a dot for Buffalo on this. And then I take the location you picked and actually go map it, and it ends up in Batavia, and you lose a point on the test because of that. The source data was not precise enough, and this project manager didn't really understand that and was pretty upset. He also had he explained the purpose of the data in the first place, the GIS person would have said, no, this isn't accurate enough. So hopefully those stories help convey the importance of precision, and there's some more slides on that coming up. Accuracy is defined as how closely does data match its description. And that's more what you might think of as error. And accuracy falls into two main components in GIS data. Is it where it says it should be, and is it what it says it should be? Where it says it should be, I call locational accuracy. Now, if I put a dot on the map and say this is the North Campus, is the dot where it should be, or is the dot somewhere else? That's locational accuracy. And as we'll see in a few minutes, people give ranges depending on the source data. Because I know the scale of this map, if I made you put a dot on where Buffalo is, I know how precise you can do that on this map. I can give an estimate of how locationally accurate your dot will be. And we'll have a slide on that. I can say, well, if you try to place Buffalo on this map, your dot will be plus or minus 20 miles based on the scale of the source data. Versus if I go try to locate City Hall with a GPS device or a survey, if I use a survey equipment and try to locate a specific feature in Buffalo, I might be down to a centimeter because of the source data. So you can use the source data to provide an estimated accuracy of your point, and we'll talk about that. The other, that's locational accuracy. How locationally accurate, if I say the desk is here and it's there, wrong, and I'm off by 5 feet or whatever that is. Attributional accuracy are the attributes that are in the GIS data set correct? So locational accuracy, I'm claiming the desk is over there. I'm wrong because it's here, not there. I might claim the desk is green. I'd be wrong again, it's not green. That's an attributional accuracy issue. So that I always ask that question, and then it's a fairly basic question, but it's important because those are two things about the desk that can be very wrong, but they're quite different in the sense the location versus the attributes. Any questions? Here's another. So here's our kind of philosophical general definition of error. The difference between how a feature is measured and its location and attributes about it in reality. So again, if I claim it's over there, I claim it's green, that's an error. And another way to put it would be values in the database that are incorrect versus being located on the wrong spot. A question I'm sure to ask on the next quiz will be, what's the difference between locational and attribute accuracy? The only reason it won't be in there is if I forget, which is another question. Because I think that's an important thing to ask. Another thing, something that comes into this is uncertainty. What is your confidence in the data? your data may not be wrong, it might be incomplete. And this happens all the time. And also kind of in that is the fact that is what is your confidence in the data set? That goes back to this precision. With metadata, we'll talk about metadata. People that create data sets should provide a metadata file so that you as the user know what is the precision or what is the confidence. Can I rely on this desk to be here, or should I not be too sure about it? But one of the problems with uncertainty is you may deal with a data set where data is incomplete. I'm going to go all the way back to the crimes. I think I went too far. So let's say that looks like Forest Avenue. There's no crime there. Is that because there was no crime there? Or is it an error? And if it is an error, did someone put the crime in the wrong spot? Or is someone not finished yet? So incomplete data is another type of error that you come in with all the time. Or did the person that created the data set not enter something because they don't know? Are they saying there were no crimes at that spot? Or are they saying we don't know? Or a third thing, we're not done with this yet. We haven't got to that. So there are three different possible explanations for that blank spot. Pretty uncertain if you think about it. So I went way ahead. Often you'll see a key value to distinguish between data not entered or unknown data. I've seen this in world census data. Some countries provide very detailed demographic breakdowns. How many people live in the United States or in Germany that are 30 to 35 years of age? And some countries may provide that information. So let's say you get to, let's pick Uganda, and there's a 0. Is there a 0 because there are no people that's unlikely, but bear with me. There are no people between 30 and 35 living in Uganda? Or is it a 0 because we didn't finish entering it or we don't know? So often data providers will create a key value, a value that you know is wrong, to indicate the lack of data. And you'll see a lot of times it's some sort of negative combination of 9s. So that would be a key value if I am preparing a data set of 32-year-olds of the world, and I can't find the answer for Uganda. Rather than put 0 and have the person speculate, well, maybe there's a freak of demographics, there are no people age 32 in Uganda, I might put -9999. And that's a key to the user. Obviously, it's not possible that there are -9999 people. So as a user of this data, I see that and I know this data is missing. It's not that the actual value is 0. I don't know the data. The person creating the data set doesn't know. Probably a better example where it would be more important is, and where I see this more, would be chemical sampling. So you might have, you're sampling for a PCB or something bad in all these locations, and you're getting a value on one particular, they sample thousands of points, so if someone dropped the vial and it shattered or spilled their beer in it or something, a lot of bad things can happen, and so now we don't know what the value is there. That's pretty important to just to blow off. So rather than putting 0, you'll see in chemical data a lot like a -99 to indicate that we messed that up. But in that case, I don't want to try and claim, oh, there's no PCBs there, by putting a 0. This location might actually be a 0. So I need a way to distinguish between this location where it tested clean and this location where I was tired, I dropped the vial, and now we don't know what it was. Does that make sense? That all plays into uncertainty. So we'll go through a few of these slides, take a break, and come back. Break between now and 8 sometime. We'll talk about where do these errors come from? What causes data to not be perfect? And it comes from a variety of different sources. And some of these things I said, error is probably too strong of a term in some cases. The error could be from the data. The error could be on you for not using the data the way you should. Over-interpreting, like the person that took the pipeline that was mapped and expected it to fall exactly where it really is. Errors contained in source data that cannot be eliminated are called inherent errors. And we'll talk about a bunch of inherent errors here. Maybe after inherent errors we'll take our break. An inherent error is part of the mapping process. It's not someone typing in a wrong value. It's things that are inherently causes of error when creating data. And early in the course, you remember SAD, shape, area, distance, direction. I mean, that's an error if we think about it. We talked about maps being distorted. And this error, I think this is a repeat slide from early in the course. You know, 3 different projections in the United States, things don't line up at all. So map projection might be a cause of error. We dealt with this just about a month ago. Remember our projection discussion? We're working for a natural gas company, helping them locate a new natural gas pipeline. And we're not the only ones working. There's a lot of different companies working for them. We did an analysis using data in a universal transverse Mercator, that UTM. That was one of the test questions, where we were calculating acreages of wetlands within a certain corridor. Another company used Pennsylvania state plain. And if you might remember, we talked about the difference between state plain and UTM back in January. Their number was different. It caused all sorts of fun. Who's wrong? Neither one of us, I like to say they were wrong, but in reality, neither one of us were wrong, neither one of us were right. We're both using a map projection that was slightly different, and we got a different number of a different total acreage of wetlands simply because one company used the Pennsylvania state plain projection, our company used universal transverse Mercator. And the client didn't really do a good job of organizing and saying from the beginning, okay, you guys all use the same projection, and that was the cause of that disparity. So that's an inherent error, map projection. That's not something that can easily be resolved. In a case like that, you need to pick one and justify it. So that's an inherent error. We didn't run the analysis wrong, neither did the other company. We just used different data and a different projection. Does that make sense? These can be the trickiest because there's no, like, oh, here's how we solve this. It's not like I just typed in a wrong number and we just fix it. Another inherent error is generalization. It's not necessarily an error, but when you're creating a map, decisions need to be made about the accuracy of the map and what can be viewed. So this is 3 different views of the same coastline. Which one, I mean, everyone would be inclined, me included, to say this is the correct one. But at certain scales, you wouldn't be able to tell the difference. This isn't incorrect, it's just a more generalized view of the coastline. Let's see if I can get Google Street. Often both on internet mapping or even in a paper map, it's impossible to represent every little undulation and change over time. I mean, if you look at this, look at the shoreline of New York and Lake Ontario. You've never been up there. Is it really perfectly straight? There's very little inlets and spits. Google doesn't map that. Is that wrong? It's not necessarily wrong, but at this scale they don't show it because you wouldn't be able to tell anyway. So what this project manager did was wrong was take something like that and interpret literally. So it was looking at data at the wrong level of generalization. So that's more of an incorrect use of data. If I, okay, does work. Watch Toronto, especially. Watch the Gardner Expressway here. If I zoom in real fast, notice. Oh, it's screwed up. For quickness of display, Google switches to a more generalized road. And then when you zoom in, it switches to a more detailed depiction of the road. And let me try that again. If you zoom in sometimes really fast, you'll still. I'm going to go to a different city because now it's going to cache that. Let's try Columbus. If I zoom in, you see that there? It was like real jagged, and then it switched to a more detailed road. That's switching generalization, in this case for quickness of display. If they tried to draw every little minor shift in the interstate, it would still be drawing. So it's not incorrect. It's just, but it's not as detailed. There, over there it switched. See the sharp. It doesn't do it again because it caches the data. It's a one-time shot. So that's generalization of data. It's not just on the internet. If you have a Ram McNally Road Atlas and you open up the page for New York State, Interstate 90 between Buffalo and Rochester looks real straight, but it's not. It curves around more. Even in the creation of a paper map like a Ram McNally, they're generalizing data. It's not going to matter anyway, because at the scale of a map of New York State, even if they did take the time to draw every little minor shift, it wouldn't really be readable, and it might confuse the reader. So using generalization is another inherent error when using a map. Using the map at the wrong, yes?
Is there any rule for the generalization?
Is there a rule
For the generalization?
for generalizing?
Yes.
It depends. That's a good question. It depends on the use of the map. I mean, there are algorithms, which I don't really get into in this course. There's algorithms for how to generalize. How do you go from this to here? But the rule would depend on what you're using it for, so it would depend on the scale of the map. If you're looking at a coastline is a good example. There's a very generalized view of the coast of Maine versus specific. So it depends on the requirements of the project, and hopefully that's a good enough answer that there's not specific, like a one rule fits all. And that actually is a good question, because we will often, when we respond to a proposal to do GIS work, there often may be rules about generalization or things in that proposal. Like a Navy project we're working on right now has such a rule that anything we map should be within a meter of reality. So they actually provide to us a data standard. And so that helps play into how much we can generalize. Hopefully that answers the question. There's no one size fits all, but often that is something depending on the project. Another inherent map error, map age. This is a poor screenshot showing a community in England I think has grown over time. Are you looking for things on the map that have occurred since the map was produced? Erie County Water Authority has a polygon-shaped file of buildings. It was actually created in 1990, and I hope some of you weren't born in no, you could have been, couldn't you? You all lose 10 points for that if you are. So some of you may have been born in 1990 or even sooner. I don't want to know. They haven't updated since 1990. There was none of this Google with aerial imagery, so this building layer was very important. In the ensuing 25 years, the people just look at Google and see buildings in air photos, so they haven't really updated this layer at all. But what happens all the time is someone will request this building layer from the water authority. They'll clip out their study area, send it to them, and next comes the phone call, my building's missing. Like, yeah, we haven't updated it since 1990. So that's an inherent, again, the layer, the data's not wrong, it just isn't updated. And if you're doing a study, if you're doing a historical study, it works fine. If you're studying an area that hasn't changed much since 1990, which is a lot of this area, it's fine. But if you're wanting to look at new subdivisions, new buildings in Amherst, it's not fine. So an inherent error in that case is the map age. Or, okay, we'll get to that guy and stop. 2 more slides and we'll take a break. So everyone understand the map age can be an issue. You're looking for things on your map that didn't occur until after the map was made. Yes, a question like list some inherent errors is always a good quiz question. In this case, area coverage, assuming that the coverage in the data set is complete. I'll pick on the 1990 buildings again. If you're from this area, you might know Erie County Water Authority actually doesn't serve the city of Buffalo. There's a separate water department. The city of Buffalo has its own water department. So they never went through the expense of creating the buildings for the city of Buffalo. The building layer just covers the suburbs serviced by the water authority, which are most of the suburbs. So sometimes people will not read the fine print. They'll ask for the buildings, and then the phone call that you get is, Buffalo's missing. Well, it's not missing. They never did Buffalo. Here we see, here's a base map of buildings out on Long Island at the Nassau-Suffolk border, the 2 counties that are on Long Island. The building layer was only available for Nassau County. So there's a big gap, there. If you didn't carefully review the information about the data, like its extent, you might conclude that there's no buildings there. But that conclusion would be incorrect. This is actually part of Suffolk County, and the data set doesn't cover Suffolk County. So this map is wrong. There's an error on this map because the data set is incomplete. So you see the difference. It's not necessarily map age in this case, but it's a case of your data not covering your entire project area. Does that make sense? So that's what you're seeing here. I put the parcels on this just to show there probably are houses on each of these properties, but they're just not shown because I only have buildings for Nassau County. I don't have buildings for Suffolk County. Appropriate scale. This is very related to, I probably should have put this slide right after the generalization slide, but very related to the generalization problem is the appropriate scale. So here are 4 views of Sapporo in Japan at very different scales. And I gave you the same effect by zooming in and out. I mean, looking at the United States at this scale versus even that scale is very different. So saying I want to map where are good fishing locations along this river, I wouldn't try to determine that from a map like this. That seems obvious, but I chose an extreme example to try to make the point there. So here are 4 different views of Sapporo, Japan, from 1 to 3 million, where you can see that kind of the northern island of Japan, right down to 1 to 10,000, where we can actually make out buildings. So if your project in Japan is analyzing demographic shifts or business along in this section of the city, you would choose source data that was captured at this scale, not this scale. It goes back to the example of trying to pin Buffalo on the world map. If your project, don't always assume, I mean, I'm guilty of the same thing right now, assuming that the larger scale data is always better. If you're doing a climate analysis of climate change in Japan, how winters changed in the last 20 years in Japan, you don't need data like this. More generalized data is appropriate. and probably better, is diminishing returns. And if you try to analyze data to that level, you're analyzing things that aren't necessary. Does that make sense? So sometimes this is the appropriate data set. I don't want to suggest that I'll always go for the most detailed, although often that's what you would need. So depending on your study, data that was developed at a particular scale will be most appropriate for what you're trying to do with your project. And the project manager who gave this GIS person data at this scale to digitize, his problem was he gave them data to create using this as a source and then expected this kind of accuracy. And it's just not going to happen. On a 1-to, the Water Authority did that too. When they created their GIS data, before GIS they had 1 to 400 foot scale, so 1 to 4,800 maps of water mains in western New York. And so what they would do, if this is Main and Transit Road, and there's a water main going here servicing the businesses there, and sometimes there's a hydrant right here, what they would do is say, well, that map's kind of busy. I'm just going to move this. This is before computers. A lot of these maps were done in the 1960s and 70s. I'll just move that hydrant a little bit so it's easier to read on the map. But what could go wrong? Well, if they moved it 1/4 of an inch, like that much, it's 100 feet off. So then 1990 comes around and an innocent GIS analyst, myself, start digitizing off of this, and they're like, wait, this is way off. Why? And then we realized they had done that. So in a sense, we didn't capture the data off an appropriate scale. We should have captured it over off a larger scale now. And that's what happened when the project manager gave. So don't trace this line and then they expect it to fall. It'd be like tracing this street and expecting it to line up exactly. Let's take a break now. We'll come back. There's not too much more. Come back and wrap up.